So chapter 4, if it were up to me, if I worked for the textbook company, I would say chapter 4 should be called Newton's second law. Newton's second law is what it's all about. What does Newton's second law tell us? Newton's second law says that F net equals ma. The net force on an object equals mass times acceleration. What's another way of saying that? The sum of the forces equals mass times acceleration. Net force and summation of the forces, it means the same thing. It's identical. Okay? Now, if an object is not accelerating, if you look at an object and it's not accelerating, what does that tell you about the net force? If your A is 0, then what must be true about net force? Net force must be 0. And there's a word that I want you guys to know. You have to know what this word means, because if you see it on the quiz or on the AP exam, or many of you are going to take the SAT-2 for physics, you have to know what the word equilibrium means. The word equilibrium means there's two ways to describe equilibrium. The first way to describe it is you could say, oh, equilibrium is when acceleration equals 0, right? What's the second way to describe equilibrium? You could say, oh, equilibrium is when the net force equals 0. It's the same thing. If your acceleration is 0, then your net force is 0. Okay? Now, the majority of the homework problems, with the exception of the first few, I don't know, I haven't looked at the homework set since last year, but the first few problems in the homework set, this doesn't really apply. But once you're a third of the way in, you're pretty much going to be following these 3 steps over and over and over. So how do you do your typical force problem? The first thing you're going to do is you're going to draw a free body diagram. What does a free body diagram show? All the forces acting on an object, and you're going to draw those forces as arrows because force is a vector. Okay, so always start with a free body diagram. Then secondly, you're going to sum forces. Who told us about the summing of forces? Newton. It's Newton's second law, right? What does Newton's second law tell us about the summing of forces? The summation of the forces will always equal mass times acceleration. And you're going to do this for the x direction and the y direction separately. Just like we did with two-dimensional motion. From this, from last chapter on, you're treating the x direction and the y direction completely separate because they don't affect each other. Okay? And basically what you're doing in number 2, in step number 2 here, it's going to look like this. You're going to sum forces x, and that's going to be like blobbity, 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 blah. Why am I saying blobbity? Because every problem is different. Every problem is different, but when you're done summing the forces, what will you do? You'll set it equal to ma, and then that's an x acceleration. And what you did is you just wrote an equation. And then you're going to go to the y direction. You're going to sum the forces in the y. Blobbity, 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 blah. It's different for every problem. And then this will be mass times acceleration in the y. Now, what if, let's say you have 0 acceleration in the y direction. Like, see this kid here? He's pulling this box. Which way is this kid pulling the box? In the x direction. So what's the y acceleration going to be for this box? 0. That box is not going to accelerate into the sky. It's not going to accelerate into the earth. So what you can do is you can go, oh, this y acceleration is 0, right? You cross it out. So basically, it equals 0. All right, and then, so here what you would have, so going back to this word equilibrium, here you would have equilibrium in the y, but non-equilibrium in the x. Non-equilibrium just means acceleration, or as they say in France, acceleration. That's how you say it in French. Yeah, that wasn't funny. All right, so now what we're going to do is we're going to go to yesterday's problem. but I just added one little thing to it, okay, just one little thing. So this is the exact same problem we did yesterday. Kid pulling the box. The box is still 30 kilograms. The tension in the rope is 50 newtons, but what we added is friction. So now we have friction present here. So let's review friction. The equation for friction is coefficient, so that mu there, the Greek letter mu, coefficient times normal force. That's the equation for friction. So in this problem, we're told that the coefficient is equal to 0.1. So how do you think about this? Well, what is 0.1 in percentage? 10%. So if our coefficient is 0.1, what is that telling us? It's telling us that friction is going to be 10% of what? The normal force. Oh, and what is the normal force? The normal force, we talked about it yesterday. It's the force of a surface holding an object up, right? So pretty much everything in this room has a normal force, because like my water bottle, the printer, my coffee mug, if it's resting on a surface, there's a normal force. When would an object not have a normal force? Like in free fall, if you jump out of an airplane, you're not resting on a surface. If you have an object,
my car's folding. I'll be right back.
Oh, scared me. So like, let's say you have an object, like we're going to do problems like this later. So say you have like a block on a table, and then there's a pulley right here, and then you have a string going over the pulley. So if this guy right here is hanging from the string, is he resting on a surface? Nope. So there'd be no normal force. Okay? But anyway, so back to friction. So the way you think about friction, when you're given the coefficient, think of the coefficient as a percentage. So 0.1 is telling you that friction is 10% of the normal force. Does that make sense? The other thing I want to mention about friction, and I might have mentioned it yesterday, but I forget, there are two types of friction, and you'll see it in the homework set. They're going to talk about problems. We'll talk about static friction. What does the word static mean? Not moving. So there's static friction, and then there's what we call kinetic friction. The equation is the same. So what's the equation for static friction? Static friction, F sub S, is equal to mu sub S times normal force. Kinetic friction is F sub K for kinetic. It's equal to mu K for kinetic times normal force. So the equation's the same. It's the exact same equation, but I want you to be aware. Oh, and the way you deal with static friction and kinetic friction, you're going to deal with it the same way. But just so everybody knows, and you already know this from having been alive for, what are you guys, like 11 or 12? How many years have you been alive? 12? Oh, 16. Okay, so for being alive for the last 16 years, I'm sure you've had this experience where you got some giant object that you have to push. Like let's say it's in your garage, and you're like, all right, big, massive, scary looking object, I'm going to move you. And you go up to the object and you start pushing on it, right? And you're like, oh, you're like push, 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 and the thing doesn't move, right? What's keeping the box from moving? Which type of friction, static or kinetic? Static. Static friction is pushing back, right? Okay, you keep pushing, you're like, oh, I want to move this, and all of a sudden it starts to move, and it's like, oh, there we go, and it's a lot easier. You know what I'm saying? Once you overcome static friction, kinetic friction's less. Kinetic friction is always less than static friction. How many of you have had that experience? Getting the thing moving is hard, but once it's in motion, the kinetic friction is less than the static friction. Does that make sense? But the way you deal with these, the way you deal with static friction and the way you deal with kinetic friction, it's the same approach. You're going to do free body diagram, sum the forces, do the algebra. All right, so I'll give you guys 10 minutes. So it's the same problem as yesterday, but I added friction. The answer, if you do them correctly, the answer to number 1 is 300 newtons. The answer to number 2 is about 0.67. And that's using gravity as 10. In class, I'm using gravity as 10. When you're doing the homework set, use 9.8 because that's what the book uses. That way the answer in the back of the book will be right on. Okay? All right, so 10 minutes. This is just a regular diagram here. We don't want a regular diagram. We want the free body diagram. So get rid of that. And here's the ground. Okay, so we'll put our box here. So how many forces are acting on this box? Always start with your free body diagram so you can clearly see the forces. So what are the forces? Tension. We got a rope pulling the box to the right. So T, we're given tension, it's 50 newtons. Okay, what other force?
Friction.
Friction is opposite motion. Okay, friction, always opposite motion and parallel to the surface. If you're doing a problem where it's static friction, then it's opposite the attempted motion, right? Like, is it possible that this kid's pulling the box, but the box doesn't move? Yeah, so then friction would be opposite the attempted motion as opposed to the motion. So here we have friction equals mu times normal force, and then we have gravity down, force of gravity. Look, you can label this different ways. You could label it W for weight, or you could label it Fg for force of gravity. Force of gravity is the same as weight, but the way that I like to label it is with the equation. So what's the equation for weight or force of gravity? Mg. And I think that's what the textbook does. The textbook labels Mg. Okay, and then the upward force is the normal force, which is the force of the surface that it's resting on. I do Fn, but sometimes you'll see this as a lowercase n for normal force. I like Fn. That's how I learned it. And we're done. That's our free body diagram. Now, sign conventions. To the right is plus, to the left is minus, up is plus, down is minus. So there's our sign convention. So we're done with the free body diagram. Any questions on that? Okay, step 2. Step 2, we sum forces in the x, we sum forces in the y. All right, how many forces are in the x direction? 2. We got the 50 Newton and the friction. Okay, the 50 is going to be plus, friction is minus because it points to the left. All right, so you go like this. So summing the forces in the x direction, you go 50 Newton minus friction, which is mu Fn. That's the equation over here for friction. And what did we just do here? What is this? We, what? Summed the forces and wrote an equation. Now, what will the sum of the forces always be equal to? Ma. The sum of the forces always equals ma. And this a is an x acceleration, right? Because we summed it for the x. We just wrote an equation. Chapter 4, you can think about it as a write your own equation chapter. To solve the problems, you're going to have to set it up and write your own equation. Okay, in the y direction, we have normal force and mg. Normal force is plus, mg is minus. So when you sum it, you're going to go normal force minus mg equals what? ma, where that's a y acceleration. All right, now, which way will the box accelerate? Is the box going to be accelerating in the x or in the y? It's accelerating in the x. So what can we do to the y acceleration? The y acceleration goes to 0 because we don't have one. You know, the box is not going to accelerate into the sky. It's not going to accelerate into the ground. So there is no y acceleration. That goes to 0. So let's erase. We'll make this just straight up 0. But be aware, guys, even though I'm putting 0 here, is that technically equal to ma? Yes. It's just that the a is 0. Does that make sense? Okay, so now we can answer the questions. So number 1, what's the normal force on the box? So take this y equation. Normal force is going to equal mg. So the mass is 30 kilograms. I'm going to use gravity as 10. You use 9.8 for the homework because that's what the book uses. And then I mentioned this yesterday, but I want to mention it again. Why am I not making this 10 negative? Isn't gravity negative 10? Yeah. But I already put the negative in right here. I already said minus mg, right? So the rule is, once you've summed the forces, you've already done the sign conventions. No more sign conventions after you've summed the forces. So we just plug in 10 for gravity. So this comes out as 300 kilogram meter over second squared. Oh my gosh, that's a long thing to write. Kilogram meter per second squared. I wish there was a shortcut unit. Oh, there is a shortcut unit. A kilogram meter per second squared, what's that called? A newton. So we just go 300 newton. Boom. That's the answer to number 1. All right, number 2. Find the acceleration. So I need some room here. I'm going to get rid of the free body diagram so we can solve number 2. So number 2, we're going to take this x equation, solve it for a. A is going to be 50 newtons minus mu Fn over the mass. So now plug numbers in. This is 50 newtons minus 0.1 times 300, because we now know the normal force, and then the mass is 30. So this comes out as 0.67 meter per second squared. Oh, and if you're wondering what happened with the units here, look, what's the unit for this numerator? What's the unit up here? Newton, which is kilogram meter over second squared. What's the unit in the denominator? Kilograms. What happens to the kilograms? They cancel and you're left with meter per second squared. Physics works. Okay.